All right, yeah, let's look at a couple problems here. I want to go through a couple absolute, oh, there's one of them that was kind of a oops on my part. I think it's number 6 on the 3.1 practice 2 assignment. The one where it asks you to find relative extrema. I'm going to make it worth 0, so just don't do that one. You don't have, if you did it, great, but you don't need to yet. There's a couple things, really, it'd be better for us to do it like next week, when I show you some other stuff. Okay, so cross that one out. Everything else is fair game though. So what about something like this? There are a couple, like there's one with a logarithm in there. This is sort of similar to that. We're trying to find absolute extrema on 2 different intervals for this function. Okay, so let's take this function on, first let's take on that interval. But a lot of the math we do is going to work for both problems, right? So if we want to find absolute extrema, where can they exist? Critical numbers or endpoints. Good. So to find critical numbers, what do we have to do? Guys, differentiate. Good. Okay, so f prime of x is going to be what?
-2.
-2 is what we get from the first term, plus
4x.
okay, and the 4 we're getting because we have x, the derivative of x to the 2/3 is 2/3
And
x to the,
-1/3.
yeah, to the 2/3 minus 1, which would be -1/3, right? So that's going to give us a 4, and then x to the minus 1/3. Let's just write it as 1 over x to the 1/3, right? So there's our derivative. So then we want to find all the critical numbers. So where could critical numbers exist? What's one thing that could be happening? Let's see somebody raise your hand here. What's one thing that could be happening to cause a derivative to be a critical number?
The problem is undefined.
The derivative could be undefined, right? What's the other thing? Derivative could be equal to 0. Okay, so let's find those places. So f prime is undefined. Where? And why?
X equals 0.
Okay. How come x equals 0? What's going on at 0? Dividing by 0, right? We see that because I've got an x to a power on the bottom. So it's undefined at x equals 0. So there's a critical number, right? F prime equals 0 when, would you agree? Now I could set this whole thing equal to 0, but this is something I like to do. We can skip a step there. The derivative is equal to 0 when this term equals 2. Everybody agree?
Yeah.
Okay, which all we do is just add the 2 to the other side. So when 4 over x to the 1/3 equals 2, right? So what's that going to give us then? That's going to give us, I guess I could cross multiply, maybe, right? And then divide by 2. Would you agree I'm going to get x to the 1/3 equals 2 when all the dust settles?
Yes.
Okay, so let's talk about that. So how do we solve a radical equation like this? What do? Okay, we got to take both sides. We got to make this into an x. I'm going to raise both sides to the power of 3. Agreed? Okay, but when you raise both sides of an equation to a power, you got to be very careful with that. You might, I'm sure you did a bunch of this last year. I know we did a lot of this in Algebra 2. You have to be careful because you can introduce extraneous solutions, right? I'll give you an example. Like, I got to make one up here. So if we did, what if we had something like x to the 1/2 equals that's not going to work. Yeah. Oh, I'm not thinking of this going to work. Well, what if I had something like okay, I got one. What if I did this? What if I did -4? Okay. If I square both sides, what do I get? I get x equals 16, okay. And that looks like my solution, doesn't it? Is it? If I plug that back into the equation, what's the square root of 16? 4, not negative 4. That's not. Square root of 16 is just 4, right? So that's an extraneous solution. It wasn't a real solution, right? Okay? What you're thinking of, if I have x squared equals 16, then the solutions are x equals plus or minus 4. Okay. But the square root of 16 is just 4, right? So we always, my moral of the story is, whenever you raise both sides to a power, you must check your answers to see if they work. All right, so let's, if we do that, if we raise both sides, if we cube both sides, we get x equals 8, right?
What about only for even powers?
Yeah, it is only for even powers.
Okay.
But it gets, you're right, it is only for even powers. Sometimes you gotta be careful, like what if you, the reason I urge people to do this is, what if I have a fraction that has, let's say, either the numerator or the denominator is even and the other one is odd or something. Sometimes it's difficult to keep track of, does that make it even or does that make it odd, right? If you're raising, and I even forget that sometimes, like if you're raising if you're raising both sides of an equation to a power, is it the power you're raising it to that makes it even versus odd, or is it, you see, I mean, sometimes it's hard to keep all that straight. So it's just always easy, whenever you raise both sides of a function or an equation to a power, just go back and just check it real quick. It works, doesn't it? 8 to the 1/3 is 2, so it checks out. That is a solution, right? So we get two critical numbers then. We get 0 and we get 8, right? So let's make our table for, I'm just going to use this spot up here. Let's make our table for this interval first, right? So remember how we make these tables. We got our x-axis, and we're on the interval from -8 to +2. And do we get any interior critical numbers there? 0. 8 is outside of that interval, isn't it? Right? But 0 is not. So then we get f or y, whatever you want to call it, and f prime. We don't even really need this row for now, but I want you to get used to using it. What would I put down here? What goes in the f prime row underneath x equals 0? Undefined. Which is telling us that it's a critical number, right? Then all we'd have to do is just check the values of the endpoints, right? So we could, if we plug into our original function, if I plug -8 in, what am I going to get? So I'm going to get positive 16, and then I'm going to get here, I'm going to get a 4 plus 6 times 4, 24, so 40. Did I do that right? I think so. Right? You can check, but I think that's right. What about at 0? What do I get? What's f of 0? Oh, sorry, undefined. Oh, no, it's not. It's not. The derivative's undefined, the function's not. 0. What's f of 2? Something weird, right? We're going to get -4 plus 6 times times 2 to the 2/3. Who knows what that is? 6 times 2 to the 2/3 minus 4. What's that roughly equal to? 5.5-ish. Okay.
Yeah.
So we don't need to know exactly in this case, for one thing, because it's not an absolute extremum, is it? If it's about 5.5-ish, what's our absolute minimum going to be? 0, right? So the absolute minimum is happening here. And the absolute maximum is happening there, right? And we've already done all the hard work. If we're gonna use our other interval, which is from 2 to 16, our interior critical number that time was 8, right? 8 is where we had a 0 of the first derivative, so it's a critical number. And now what? So we got about, if we evaluate our function at those places, we already got something about 5.5-ish. What if I evaluate my function at 8? That should be an easy one to do. You're gonna get negative 16 plus, what if this ended up being 24 for negative 8, right? And because this is an even term, taking it to an even power, I'm gonna get the same answer. Everybody see that little shortcut you could take? So negative 16 plus 24 is 8. So I get 0.88. And then what about at 16? So at 16, what's this gonna give me? Oh, yikes, what's that gonna be? Cube root is 16. Well, I'm just gonna plug in 16. Yeah, what do you get? What is it roughly?
34.1.
About 34.1. We're not gonna get an exact answer. We could, right? We could write that out using fractional exponents if we wanted to, but I don't wanna take all the time. So we know that we're gonna get our maximum this time is at 16. Absolute maximum, our minimum is gonna be at, did I do that right? Negative 2 times 16. Are you sure? Are you sure that was right? Oh, it's not -4, it's minus, it's at 16, so we get negative 32 plus 6 times 16 to the 2/3. Try that again. Maybe it's right. It seems like it ought to be smaller than that.
2.
About 2.
F of 2 is 9.5.
No, F of 16. Other
Six.
endpoint. 6.1? Oh, okay, well. Okay, so then we got one endpoint, or, one endpoint was our minimal. The left endpoint, right? And our maximum was right here. You should say our absolute minimum was at one endpoint. Or the absolute minimum was roughly 5.5, and the absolute maximum was exactly 8. Okay? All right, so that was kind of a hard one. I want to look at one like this because it's got a trig function of, like, it's not just an x inside the trig function. It's kind of nice to see one of these. So what are we trying to do? I think I didn't write down the whole problem. I think all we're trying to do here on this one was find the extreme. Yeah, it was find the absolute extrema. Okay. So what's f prime? We got cosine of 5x.
5, negative 5 sine x.
Right, the derivative of cosine hand is negative sine hand times the derivative of hand is 5. So put the 5 out front with the negative 1. Okay, is that undefined anywhere? No, it's a sine function, it's fine, right? There's no, sine and cosine, there's no vertical asymptotes. It's all the other ones where we've got vertical asymptotes, where there's places where they're undefined. The sine and cosine are fine. It equals 0 when? When does sine equal 0? When does sine of hand equal 0? Think about a unit circle here. So if we draw a unit circle,
Yeah, 0.
sine is the y coordinate, right?
So 0.
So it'd be at that place on the unit circle and at that place. Everybody agree? Okay. So then, but that's what 5x is equal to, right? Think of this as being a theta, right? Sine of theta equals 0 when theta equals 0 or pi or 2 pi. How could we say that all those solutions at once? There's an infinite number of places where it happens, right? On the unit circle, I could go 0, pi, 2 pi, 3 pi, negative pi, negative 2 pi. What do all those have in common?
Integer pies.
They're just integer multiples of pi, aren't they? Right? So we could say something like, this happens, f prime of equals 0 when theta equals n times pi, where n is just an integer, right? So that's just our shortcut way of saying n is an element of a set of integers, right? Okay, but what is theta here in our problem?
5x.
Theta is actually 5x, right? So if we solve that equation, then this is pretty cool. 5x equals n pi. Let's solve for x. What's the result?
N pi over 5.
Okay, so n pi over 5. So it's any integer number, any integer multiple of pi fifths. Well, look on our interval here, we're going from negative pi 6, so that's like right here, up to positive pi fourths. So what are which values of n would give us critical numbers within our closed interval then? So we're going from, once again, negative pi 6 up to positive pi fourths.
Just pi.
Pi over 5 would work. If n is equal to 1, so what are some values we get then? We could say x is equal to like negative pi fifths, 0, pi fifths, 2 fifths pi, etc. There's an infinite number of them. Which ones of those are going to fall in our interval? Well, negative 1/5 pi, that's going to be down there somewhere, isn't it?
Yes.
Right? It's going to be more negative than negative pi 6. So that's outside the interval. The 0 is going to work, right? And then pi fifths, 1/5 pi is less than 1/4 pi, isn't it? So up here somewhere we're going to get pi fifths. So we get, those two should work, right? Those are our critical numbers. Okay. That's kind of, I want to go through one of those because you have to make that connection. If you're trying to, once again, trying to solve a trig function, you're trying to set the derivative equal to 0. Well, when is sine of 5x equal to 0? Sine of 5x is equal to 0 where? Well, when 5x is equal to some multiple of pi, right? Because you're thinking of it in terms of the behavior of the trig function. You would ignore think of it as a theta. When is sine equal to 0? When the angle you're plugging into sine is a multiple of pi. Then what's actually inside the trig function, we'd say the argument of the trig function in math, we set that equal to n pi. Okay? Could you have done this a little differently? I mean, you see that we could have said, yeah, so what are some values then? I could have picked negative pi, 0, positive pi. I could have picked a bunch of values and solved for each one, but you see how much more elegant and simple it is if instead you just use the solution n pi, where n represents all possible integers. You only have to do it one time then, right? Okay. So then we want to make our table. We're trying to find absolute extrema. And let's see, our endpoints were negative pi 6 and pi fourths. And our interior critical numbers were at 0 and pi fifths. You know, I usually try to get them like somewhat proportional, so it doesn't have to be exact, right? But they're about where they should be on this number line. And then those are places where the derivative is equal to 0, so those are critical numbers. And then all we do is just check the endpoints, right? And that's, well, you guys can finish that, that's what we'll do. Right, we'll plug the endpoints and the critical numbers into our original function and just see what we get. Okay? Make sense? I won't bog you down with that detail. Okay, what about this one? This is kind of, we don't have to even do this problem, we got to talk about how this one is a good application of the calculus that we're talking about. Stone is launched vertically upward from a cliff 192 feet above the ground at a speed of 16 feet per second. So this looks suspiciously like physics stuff, doesn't it? Okay, its height above the ground, t seconds after launch, is given by this kinematics equation, right? So S of t, it's a function of t, height is position of t equals that. For 0 to 4 seconds, right? There's the interval we're looking at, okay? When does the stone reach its maximum height? Well, that's just an absolute extremum problem, isn't it? The absolute maximum problem, right? And all we're gonna do here really just is represented by this. I've got T, I've got S, and I've got S prime, right? S dot, I guess I could say in this case, right? If I want to. My interval goes from 0 to 4. What would I do to find my critical numbers? Take the derivative and set it equal to 0, right? Wouldn't be a big deal. S prime equals negative 32t plus 16. When's that equal to 0?
0.
No. Say it again.
Okay.
1/2. Yeah, everybody agree? If I set that equal to 0 and solve, I get 1/2 for my one critical number. And then all I'd have to do is just compare the values of the height, of S at each of those places, and the biggest one has to be the absolute maximum. That's pretty cool. You can do that. What's that? You know it, yeah, you know from the context it's got to be 1/2, don't you?
Yeah.
Right. But this would show that. Okay. All right, what about, okay, this is kind of a tough one. This is the challenge question I gave you. The last one, I'll go through this one with you. At least we'll set it up, go through a couple things. I want you to, maybe I won't do the whole thing, because I want you guys to get a little practice on it. But you see why this one's tough? We're supposed to determine the critical points on the given interval, and just the critical numbers is all we need, just the values of x, and then determine absolute extreme values. So it is an absolute extremum problem on a closed interval, right? They give us our closed interval. What's so tough about this one? Yeah, that's a weird derivative, right? That's not in the tables. That's not one of our standard forms. We got cosine taken care of, tangent, we know quotient rule, we know log, how to do derivatives of natural logs and exponential functions, but we don't know that one. You're right, we got to use logarithmic differentiation, don't we? Right? So it's a good application of the stuff that we just talked about. So we would just rewrite this as y. Oops. Just rewrite that as a y, and then what do? Yeah, log both sides, right? If we log both sides, I'm going to get the natural log of y equals the natural log of that whole thing, right? Now, if I'm going to do the natural log of this whole thing, well, first of all, I've got a product, don't I? Right? So the natural log of a times b, remember, is natural log a plus natural log b, right? So I've got natural log 4 plus natural log of 3x to the x, right? Okay, good. But then what can I do with this one? There's another. Bring the x down. Yeah. So log y equals log 4 plus x log 3x. Now that's a little better, right? Now we can differentiate that pretty easily. So what's the derivative of log y? Right? Derivative of log u is u prime over u. So if u is y, it's y prime over y. Derivative of log 4?
0, 4.
And we don't even need the 4 there, right? Because log 4 is a constant. It's a fancy looking constant, but it's just a number, isn't it? The derivative of any constant is always 0. So that one just goes away. And then what about this guy? That's a product rule, isn't it? Good, so we've got x times the derivative of log 3x. Well, what's the derivative of log u?
1 over u.
Almost.
U prime.
U prime over u, right? So u prime is going to be 3, u is 3x, right? 3's cancel, okay? And so the x's will cancel, won't they? Plus, the other part of that product rule, because we got two terms in the product rule, would be log 3x times the derivative of x, which is 1, right? So what's that give us then? Y prime over y equals x divided by x is 1 plus natural log 3x. Okay? I'm trying to solve for y prime though, so what's my last step? Multiply each side by y. And, okay, what is y? 4 times 3x to the x,
Yes.
right? So there's my y. So there's y prime. Okay, now, this is where now I wouldn't blame you if you looked at that and said, wow, that's really looks terrible. How am I possibly going to know where the critical numbers are of that? But don't panic here, because we're doing this on a closed interval. We only care about the critical numbers on our interval. And our interval is from 0.1 to 1 inclusive. Where do you suspect this function might be undefined? And you'd be right to assume that. It's 0, because how could you take 0 to the 0? We haven't learned this yet. This comes much later in calculus, but that's what we call an indeterminate form in calculus, right? That's a possibility. You wouldn't know that for sure, but does it even matter? It's not in our interval, so who cares, right? In our interval, is this first factor ever going to be a problem when x runs between 0.1 and 1? That's going to be fine, isn't it? I'm just going to end up taking some number to a power for all those values of x. That's fine, isn't it? There's nothing to worry about there. There's no place where I'm going to have to divide by 0 or do something crazy, right? Obviously, natural log is defined for all positive numbers, right? So this is in the domain of natural log too, so we're fine. So we know for sure then, just by inspecting this thing on our interval, y prime is nowhere, is how we say it in math, is nowhere undefined. Okay? Right? So we're good there. No, there's no critical numbers coming from that. Now, where could it possibly equal 0 though? If I set y prime equal to 0, where could that happen? I mean, it's factored, isn't it? I've got a factor times a factor. By the zero product property, when would 3x to the x equals 0? Well, no place on my interval, right? The only place that could possibly equal 0 is when this equals 0, right? When 1 plus log 3x equals 0, right? So what is that going to give us? If 1 plus natural log 3x equals 0, we can solve that. I mean, it's kind of weird looking, but we can solve that. So all I I really need to do is just subtract 1 to the other side. So natural log 3x equals -1. How do I solve a log equation? How do I undo a natural log? Okay, exponentiate both sides, right? Take e to the power of both sides. So 3x equals e to the -1. Well, e to the -1 is what? 1 over e. So if I multiply each side by 1/3, x equals 1 over 3e. Is that on our interval? Is that on the interval from 0.1 to 1? It's got to be, right? E is like 2.7 something.
Yeah, so just about 1.12.
0.12-ish, something like that. It's going to be something like 1/8, something like that, right? 1/8 is bigger than 1/10, so that's on our interval, right? So all we'd have to do then is just check the value of the function at that one place compared to the endpoints to find our absolute extremum, right? That's a tough one. And there's a lot of good, like, pre-calculus math going on there. It's good to review. All right. I'll let you guys finish that one up. On here, I think we can skip that. Okay. We'll come back to this one. I want to make sure we do this one. This is a cool one. Cool application of the mean value theorem. This is pretty cool that you can do this. You could probably convince yourself of this conceptually, but there's a mathematical proof. This is a good example of where an existence theorem comes in handy on a proof. So when an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit. 5 hours later, the core temperature is 390 degrees Fahrenheit. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour. Okay? So that sounds an awful lot like a mean value theorem problem, doesn't it? Right? Does the mean value theorem apply here? What would the function correspond to here? What's going to be the dependent variable? If we had to turn this into kind of like a math function. Time, right? Time is passing, and what's happening? Temperature's decreasing. So what would be the dependent variable, or the function? Temperature, right? So we've got temperature as a function of time, right? So is the temperature function, what would have to be true? It looks like it's 5 hours later, so what would our closed interval be here for t? 0 to 5, sure, right, 0 to 5. So we've got 5 hours later, so we already know that we're on the interval from 0 to 5. So what has to be true for this to meet the criteria of the mean value theorem? It has to be smooth, which means it has to be continuous, right? Okay, well, does that make sense? Is it possible that at some point, now just think about the physics here, is it possible that as this thing cools down, it's going to be cooling down, and we're looking at the temperature, and then instantaneously the temperature is going to go through some macroscopic jump? Like it's going to go from 1400 degrees Fahrenheit to 1300 degrees Fahrenheit with no time passing. Is that possible?
No.
It's not the way the world works, right? So we know that just because of the fact that this is a cooling object, the temperature has to be continuous. You can't skip temperature. That just isn't, physics doesn't work that way. We can pretty much convince ourselves of that intuitively, right? What about the differentiable part? The rate at which the temperature's decreasing. Does it make sense that instantaneously the rate's gonna change? Once again, that's not the way things happen, right? The rate at which the temperature's changing is gonna always be changing smoothly also, right? Because it's a physical object, you can't go through those macroscopic jumps. Only place in physics you can do stuff like that is like in quantum mechanics, but normal physics doesn't work that way, right? So this has to meet the criteria of the mean value theorem because it's a cooling object. It's got to go through all the infinite temperatures in between 1500 and 390. It's got to go through them smoothly, right? So then what does the mean value theorem tell us? Well, it's telling us that the rate of change, the average rate of change, at some point the function has to go through its average rate of change. right? The instantaneous rate of change has to equal the average rate of change. What is the average rate of change? So, what's that gonna be? We call that, maybe let's call it change in temperature over change in time. How much does the temperature change? Because it's like saying T of 5 minus T of 0. Capital T is temperature, right? Over 5 minus 0, right? Well, actually, it's 390 minus 1500, right? Over 5 minus 0. So what must that give us? That's going to be 1100 divided by 5. What do you know? That's about, actually, is it 11? What is it? It's, these guys help me out here. 1110?
Yeah.
So 1110 divided by 5 is 222, isn't it? Negative 222 degrees Fahrenheit per hour, right? So then, doesn't this guarantee, the mean value theorem guarantees that at some place between 0 and 5 hours, the instantaneous rate of change has to equal, at least at one place, it has to equal negative 222, so it's decreasing at a rate of 222 degrees Fahrenheit per hour. Has to happen at least once. Right? Make sense? Okay? I just thought that was kind of cool. All right. We're not going to get anything, not enough work time, so let's try one more, and then I'll give you guys a work day on Monday. We'll work together on this stuff. So for what values of A, M, and B does this function satisfy the hypotheses of the mean value theorem on the interval from 0 to 3? Right? So once again, we're just thinking about what are the two criteria. It's got to be continuous, right, on the closed interval. Right? It's got to be continuous. On the closed interval from 0 to 3. Okay? So for this thing to be continuous, all three parts of this piecewise function have to meet up. Agreed? So then what about between 0 and 1? What does the limit of f of x as x approaches 0 from the right have to be? Because think about this. Look, we've got 0, the top row, the top piece of this function is what's happening at the 1x value 0. The middle piece of the piecewise function is where the function's defined when x is between 0 and 1. And the bottom piece is how it's defined when x is between 1 and 3, including the endpoints, right? So we know that where we join up right here and right there, where those pieces of the function come together, they have to meet up, don't they, right? So if we color code this, how about? The blue junction right there tells us that the limit of f of x as x approaches 0 from the right, from values bigger than 0, has to equal what? Has to be 3, because that's the value of the function there, isn't it? Right? Has to be 3. Well, what's that give us? That's going to be this piece of the function. So the limit of negative x squared plus 3x plus a as x approaches 0 from the right has to equal 3. What is that limit? If I evaluate that limit when x approaches 0, doesn't matter from which direction, what am I going to get when I plug 0 in there? 0 plus 0 plus a, so I get a equals 3. A has to be 3, doesn't it? There's one constraint that we know, a has to be 3, okay? So that tells us that this middle function is negative x squared plus 3x plus 3, right? Okay, what about the bottom one down here? So we know that the limit of the function as x approaches 1 from the left has to equal the limit of the function as x approaches 1 from the right, doesn't it? So that's going to be the red boundary. So if we're approaching from the left, that's going to be the middle row, right? So we get the limit of negative x squared plus 3x plus 3. We can plug 3 in for a. As x approaches 1 from the left, has to equal the limit of the bottom row, mx plus b, as x approaches 1 from the right. What's that tell us? As x approaches 1, we get negative 1 plus 3 is 2, plus 3 is 5, agreed? We get 5 equals m times 1 is m. Okay, inconclusive, right? What else do we need to consider, though?
The slope of that one.
It's got to be differentiable, too. It's got to be differentiable on the open interval. So there's the other criterion, right? It's got to be, if the function has to be, f is differentiable, on the open interval from 0 to 3, right? So what's that tell us? I'm going to run out of time, all right. Calculus needs to be like 5 minutes longer. You don't think so?
Just block, schedule, and time.
You know, in the clinical, we used to have that. We had 7-minute blocks. We had calculus, I think the calculus and physics back in back. That's awesome. So they always went into each other's brains. Where'd you do that? 2-hour block? You'd have to break that up a little bit. Yeah. You'd have to break that up. What's that?